So one way to visualize the definition for this Riemann sum is to consider the special case in which the path R of u is actually a two-dimensional path in the plane xy. Okay, so remember, this is a simple case, and the reason why we choose this simple case is that in this simple case we are able to visualize everything in a graph like I'm doing here. But in general, it's not possible to visualize it when the curve is in 3 dimensions. This is only possible when this curve, so this curve here, which is our curve, is lying on the xy plane. Okay, so it doesn't have a z component. So then you can see here that I have indicated the different values of u, u1, u2, u3, u4, up to un on each of these segments. And the segments are of length L1, length L2, L3, L4, and Ln. Those would be the segments. Actually, delta L1, delta L2. Okay? So now we are saying that we are getting, so we are doing a sum between y equals 1 to n of f at ui times the length of the segment. So what does f at ui mean? So let's assume that we are integrating a function f of xy. Okay, so that's the function we're integrating. Okay, and this curve is on the xy plane in this case, in this simple case. So what we can do is that we can plot our function f of xy as this yellowish surface here, right? So this yellowish surface that is wavy, this is our function f of xy. As you know, for a two-dimensional function, it represents this kind of surface. So now it means that for every point, for example, when u equals u1, you can find the point R of u1, which would be this point here in the xy plane, because R is a curve in the xy plane. Okay, so R will be a function x of u and y of u. So for each value of u, for example, u1, you can find x of u1 and y of u1, and you are at some point in the xy plane always, yeah? So we have at some point here. And therefore we can evaluate the function at that point. Okay, so we are doing f evaluated at R of u1. Okay, and what we can do is we can call this f of u1. And this f of u1 is this height here. Okay, so it's the vertical height between the xy plane at this point and the surface that represents our function f of xy. So that will be the value of the function at that point. Okay, so this is this height here. Okay, so that height here is f of u1, which is the first term in the sum. And this height is being multiplied by delta L1. And delta L1 is this width here. Okay, so we are multiplying this height times this width. So what are we doing? It's as if we are calculating some sort of rectangle whose height is equal to f1 and whose width is equal to delta L1. So let me show you this in a Mathematica script for a different curve. Okay, so here it is. So you can see that we have a curve which is this this blue curve here, which is in the xy plane. And now I have divided it into segments, and you can see these dots representing the limits of the segments. So now if I calculate the function, and the function is some surface on the z-axis. So if I calculate the function at the center part of each of these segments, and I plot the rectangle, which would be the height of the function, multiplied by the length of the segment. So I get the area of this rectangle. And I do this for all of the segments. In this case, I only have 4 segments. Okay? So these are 4 segments. So of course, if now I start increasing the number of segments by making delta L go to 0, in the limit, what I get is this perfectly smooth curve, and I'm calculating the area of this smooth shape here. Okay? So let me go back to our example. in the limit in which I do infinitely many segments with the limit when the segment goes to 0, so basically I'm doing the limit when the length of the segments goes to 0, so then I end up calculating this area here that I am highlighting in dark yellow, okay? So remember, each of the segments, I'm multiplying them by the height of the function, and therefore I get the area of the rectangle. I do many rectangles, and in the limit, when I do infinite rectangles, this becomes a smooth thing. It's no longer made out of rectangles, it's completely smooth, because we are doing a limit. And therefore, the area of this, of all this region here, which is actually like a surface, like a curved surface, right? So the area of that curved surface is equal to the integral of f dl. Okay? So that was a very hand-wavy explanation, and I'm sorry for that. I don't think I can do any better. What I did see is that Wikipedia has a very nice animation. Let's have a look at it. So here we have a function f defined on x and y, and the function is given by the color. And now we define a path from A to B, and this is the path, the curve C. Okay, it's going from A to B. So now the function, as you can see, it's a three-dimensional function. So now we plot the area between the path and the function, which is the blue curve. And now if we straighten that up, we end up calculating the area of this blue thing here. I really like this animation, so this area will be equal to the integral f ds. Okay, I think it's very neat, so I encourage you to go to Wikipedia. If you go to the article on line integral, you will find that animation here. Okay? Good. Thanks for watching. See you in the next video.